Hello guys, how are you? You guys can see my screen?
Yeah.
Okay, so let's start. So today we're gonna, explore a new topic called probabilistic roadmaps. Okay, it's not a search algorithm, although it's a way to construct a map. Okay, so assume you have some environment in which the robot will navigate from some place to another, but there is no map for that place. So using algorithms like probabilistic roadmaps, the robots can build their own maps of the space. Okay, till this moment, all we considered only one map, which is a very simple grid map. Okay, just like chessboard, something like this. And the robot moves from one square to another or one cell to another. Okay, probabilistic roadmaps, it's another way or an algorithm for the robot by which it can build its own map, created from scratch, we can say. And it's very useful for large maps. Because for large maps, if you construct it using grid cells, you may use a lot of memory. Okay. Okay, so let's see what is this probabilistic roadmaps look like. So as I said, it's a way to discretize a map and build it from scratch. And it's really very useful when you have a higher number or very high number of dimensions. Okay. One may ask how we can have dimensions larger than 3. So here, the dimensions is not only the environment that you have. Maybe how the robot will move itself is a dimension that you can add to the system. Okay, if you, for example, if you have an arm for a robot, this arm, the flexibility of this arm or the degree of freedom of this arm is something that is adds to the complexity of the map itself. Okay. So basically, we use probabilistic roadmaps to build maps from scratch, and usually these maps are less memory depending or cheaper to implement than grids that we just considered so far. Okay. Any PRM algorithm has two phases: the building phase or creation or map creation phase is the phase that I'm just talked about. Is that you don't have any map for you just know the robot just knows the obstacles, okay, the obstacle locations, and based on that and some other parameters, it will build the map. Okay, basically in that phase we assign for a robot while creating its map some maximum number of nodes. These nodes will be used to represent the map around the robot. Okay, so it will generate nodes randomly in the space around it. okay, with maximum number of required nodes as a parameter. So for each new node it generates, it checks the closest nodes. So it generates some nodes. This node may, so for example, if these are the nodes that are already in the map, okay, it generates a new one. Then based on some predefined distance, okay, for example, 50 meters, it will searches for the closest or the neighbor nodes within these 50 meters. Let's assume, for example, this is a new node. These are the old nodes. It's, you know, this is for example 49. This is for example 60. This is for example let's say 50. So the closest node within 50 is actually this node and this node. Okay. Then based on another parameter, which is the maximum number of nodes to connect. Okay. So here there are two nodes within the 50 meter range. The more you connect, the more flexible will be your map, but the more memory you will use. So you may define a maximum number for the nodes to connect. Even all the nodes, even there are many nodes, more nodes within the specified range, we can say. So let's say M is 1, for example. So you will just connect to this one, to the 49, to the closest, and not this one. Then looks like the map will be just like a graph for us. Then add this node to the graph and this edge as well that you created. One note here, the word that I used here is valid node, because maybe you have obstacle like this. If you have something like this, again, these two nodes are within the 50 meter range, but you can't connect to that one. So at that time, you only will be connected, or you connect your robot to that one only. Okay, this is why I'm using valid node, because there might be many nodes within the range, but some of them there's an obstacle between obstacle between the robot and this node, so you can't connect them together using an edge like this. So you can't add this edge to the graph. Once you build this graph here, then you can use it. Okay. By the way, I didn't mention any goal or any start node yet. So we are just building the graph, okay, without any prior information about the start node or the goal node. Because we are building a map. This is not a search algorithm. Once you build a map, then whatever the start location and the goal location of the map, just add these two nodes to the map, connect them to the closest node in the graph, and then use this graph with some search algorithm like A star or Dijkstra to build the shortest path. So in the usage phase, we add the start node and we connect it to the closest node in the graph. For example, let's assume this is the start node. Where is the closest node here? This one. So you connect it to this node. Let's assume that this is the goal node here. What is the closest node? This is the closest node. Then you use A star or BFS, any algorithm that you learned so far, and construct the path between the start and the goal, something like this. Okay. And here is from that particular example, you might see that this path may not be the shortest path, by the way, because it's the shortest path based on the nodes that you have. But it might be a better option if you just connect the goal and the start location like this. Okay, because you are using what's already there. It's a probabilistic roadmap, something that you create from scratch. You generate randomly the nodes. So you must use what you get, what you created. Okay, although it might be not optimal. It will be optimal based on the memory efficiency, for example, because you are not discretizing your map into smaller cells, very small cells, okay, or like a grid. So you will use less memory and less number of nodes. So the computation will be very fast. Even the algorithms that we'll use, it will find the shortest path faster, but this shortest path might be not the best option. Okay, you might build the map in another way using, for example, some random another random seed. I will show you how to choose a seed. Okay, and you may get faster options. It's a probabilistic. So the main goal here is to represent the the map in a very efficient way using less memory. Okay, that's basically the basic two advantages for probabilistic roadmaps, and we sacrifice the optimality in finding the shortest path. Okay, clear, guys?
Yeah, it's clear.
Good. Let's continue. Oops. Oh, I forgot to remove this slide. Oh, I'm sorry. Okay. Okay. So let's see some examples. Oh, it doesn't go away. Okay. Okay, so example one here. Okay, so these are the parameters that we're gonna tune, like just like artificial potential field. There was some parameters up there, okay, in this algorithm, and we fine tune this, like the speed, for example, in order to get better solutions. Here you have also some parameters that you must tune in order while you are building this the roadmap. Okay. One thing here in that map here, there is no goal or start nodes. All these red nodes here is just a nodes that represent the map. So, for example, if we choose the maximum number of nodes to connect equal to 2, that means when you generate a new node, and how to generate a new node, just to choose random variable. I mean, random x, random coordinates, random x and random y, and be sure it's within the map. It's a free space. I'm sorry, it's a free, not obstacle. So, for example, we generate a node like this, and the maximum number of nodes connect is 2. Then we connect it to the closest 2, but within the range, which is in this example 300 meters. So this length here must be this length L1 and L2. L1 and L2 must be less than 300 meters. You also define the maximum nodes in the grid. If you count all these nodes, all these red asterisks, you will find them 350. I will just ask you a simple question. What's the advantage and disadvantage of increasing that parameter? If we make it, for example, 1000, What is the problem in that, and what is the advantage of that?
Optimization of memory
Yeah.
and shortest
So
path.
the memory is bad or worse, or
Yeah,
or
memory is worse.
yes, and how about the advantage?
Shortest path is it's found
Yes, yes,
better,
yeah, that's
shorter.
right. That's right. Yes, the more you add nodes to the map, the more you will have, the more probable to have a shortest path, and also the more coverage, and that's more important. The more coverage you will have for your map. So, for example, let's give a very extreme example. If we just choose this guy to be 10, or let's say 2, just 2 nodes that will represent the whole map. Okay, and the first node was here and the second node was here. First of all these areas are not represented. Okay, and secondly, you cannot connect these 2 nodes together because there is obstacle in between. Okay, so the more of that guy, the more or the greater, okay, you will have more coverage for your map, and probably yes, you will find the more you will find shortest path. Okay, how about the maximum number of nodes to connect? If we increase it, let's say we make it 20 or 200, what we gonna gain and what we gonna lose?
I think it would be the same thing, no?
Yeah, that's right. Yes. Again, if you increase this number, the more coverage you will have because you have more connections. Okay. So, for example, if you have 3 nodes, okay, so if you have 2 nodes originally in the map and you generated a new one, and the maximum number of connections is 1, so you either connect that node to that one or that one, whatever. Let's connect it to that one. Good. Now, if we want to move from that node to that node, what will be the path? The path will be like this. We move like this, then we move like this. Also, from the beginning, if this was 2, then you will connect this node to this node and also this node. Then, if you want to move from this node to this node, you just, move along one edge. Okay. And finally, this guy here, maximum connect length, is also have the same effect. So again, for example, if we have same example, so we have 2 nodes from the beginning, then we generated this new one. Let's assume this is the distance. Let's assume this distance is, for example, 400, and this distance is 250. So you will connect this node to this node, and then if you want to move from this node to this node, you should move like this. Also, if this was, for example, 450, then you will connect this node to both the old nodes, and if you want to move from here to here, you will just move like this. One edge, shorter path. Okay. So let's see what happens if we increase each one of those. So this is example 2. I just make the connectivity 20. So here in the beginning, any node can connect only to maximum 2 nodes. Now it can connect to 20. Look at the map. You have more coverage, probably you will get shorter path lengths. But again, the problem will be the memory, because you have many edges now in the graph, and all these edges or connectivity should be stored in some array in your algorithm. Okay, this is clear, guys?
Hey, Professor.
Yes.
I'm just trying to understand max nodes. Max nodes connect a little bit better. So basically that just means like the amount of things the node can be connected to.
The maximum number of nodes that the new node can be connected to. So for example, if we have originally 3 nodes like this, then we generated a new node, and this new node, for example, was here or here, for example. Okay. And the maximum length is 300. Let's assume this distance is 200. This distance is again 200. This distance is 100. So all of them are within the range. All of them has no. So in principle, I can connect this node to all these 3 nodes.
Okay.
But assume this is 2. So I should choose only 2 of them, maximum 2 of them.
Okay, got you.
Okay. So in that case, for example, you should connect to this one, for example, and this one. For example, or this one and this is this one here. Only 2. Okay. Any other question, guys?
No, I think that's about it for me. Thanks, Professor.
Okay. So let's
quick
see.
question.
Yes.
So how would it differentiate between the distance of 200 between those 2 nodes? Which one to connect to?
Yeah, it's up to you.
Okay.
Up to you, because both have the same, same distance. So up to you. Doesn't matter. Okay, now let's, so we go back to the original one, 2 and 350 here. But now the maximum connect length is 2000. Again, we only connect to 2. But the maximum connection is 2000. So look at this. You see this edge, guys? You see this edge? There are very, lengthy edge. Let's use another color to make it clear for you. We have now very long edges like this one. Like this one. Okay? Also this one here. This one. These are very long edges. Okay, so let's, for example, see, compare it to the previous one. These long edges are not there. Okay. Finally, let's have another example with 2000. Okay, now, yeah. Maximum number of nodes in the grid is 2000. So 2 are the same as example 1, 300 as the same as example 1, and you have 2000 here. So basically, if we compare this graph here, or this map, I'm sorry, this map to the previous, to the first one, example 1, it's obvious that the other one with 2000 more dense, and you have more coverage as well for your map. Okay, but of course you will have more memory usage. You need more computation power. Okay, and of course, if you run some algorithm like A star on that particular graph here, it will take time, but it will give you a better solution because you have more coverage. So probably you will get to a better, shortest path in your graph. Is that clear, guys?
Yeah.
Okay, what else we have? Yeah. One last thing is that when you generate a new node like this one, for example, assume that the maximum number of nodes to connect is 2. This is 2. So you will connect this one with the closest 2 nodes, but they should be within the range. So assume this one and this one are within the range. Okay. Also, you have obstacle here between this guy and this node here. This is the obstacle. So clearly, we should have some algorithm, okay, to detect, you know, such kind of violation. This is violation. We cannot do that. We cannot have an edge through an obstacle. So this will be accepted. So this is the graph after we finish. It will be something like this, and we will exclude that that edge here. Okay. By the way, this is your homework. So the code that I will send to you will not have, you know, this is check. You will do that. You will do that check yourself, but it's very easy. It's not a problem at all. Basically, what we are doing is that we divide this bus here into nodes, something like this. Okay, and we check each one of these nodes are on or is on. How can we say this? If each one of these nodes, if any of these nodes are within an obstacle, like those, for example. If even one of them are within an obstacle, then there is obstacle between the start and the not the start and the node, between the new node and and this neighbor, for example. Then you must exclude that edge and don't add it to your graph. This is clear, guys, or?
Yeah.
Okay. So that's it. Let's go to the coding itself. Okay. The coding is also easy, at least much easier than the artificial potential field. You can see the coding?
Yeah.
Yeah.
Okay.
Well, not anymore, but
What?
It just disappeared right now.
yeah, it disappeared.
So let me share it for me. Something wrong. Share screen. And yes, number 2. How about now?
Yeah.
Okay. Okay. So let's have let's have what? Let's have around. So these are the original, you know, the original numbers in the example 1. There is here a new parameter that I didn't talk about. It was on the last slide. So when you are checking, you know, let's talk about this in the graph in the other screen. I'm very sorry for this. So you can see the tablet now, guys, right? So basically, when you create an edge like this and divide it into smaller points, the number of points is also a parameter. Okay, you can call it, for example, number of segments, because we certainly divide it into segments, in this edge into segments. And if any segment is inside an obstacle, then you know, we just, you know, not considering this edge. So this node and this node will not be connected in the final graph. Okay, so this is another parameter that you must, and it's very important one. It's very important. Okay, I will show you why after that. So screen 2. Now we go back to the Matlab. So it's important to have one seed, the exact seed each time. Okay, Because if we discover the problem, remember here we are generating these nodes randomly in any random place within the map, of course. Okay, so if you discover some problem and you want to debug it, it's important to generate the new problem. It's important to generate the problem again and again so that we can debug it well. So the random number should be the same each time. That's why you should fix the seed. If you don't fix the seed and you discover on some runs there is a problem, for example, an edge that crossing an obstacle, which is of course invalid, then you need to regenerate such a problem again and again so that you can debug and know the source of the problem exactly. That's why I am fixing the seed here. Choose whatever number you want, okay? And here is how you fix the seed in Matlab. It is using this function here, range of whatever. Of course, you don't need to put a new variable, okay? You can just put this number here and it will be just one line, not 2 lines. But I need to tell you that this is actually, and that this is actually, yeah, and that this is actually the number that we put here is actually the seed that will be used to generate the random number. Okay. First, let's see how much this is just for simulation. How much cells we have? Okay. So we have here 1,300 cell by 1,300 cell. Okay, it's very big. If we use the map with these cells using A star or whatever, then the map will have more than 1 million cell, and the A star or Dijkstra or breadth-first search will take very long time to construct the shortest paths. That's why we need to choose only some cells to represent the whole map. Okay, that's what we're gonna do now. Okay, so let's define an array called obstacle. Basically, I will define the obstacle in that array. Okay, and again, x, y equal to mesh grid or whatever that means for that array here, which is the obstacle array. X and y will contain the x coordinate of any cell and the y coordinate of any cell. Now here we generate the obstacles. Okay. So let me run a quick run, very quick here with you to show. Yeah, we can actually stop at some point. We don't need all of that. Yeah. So let's stop here. Okay, let's stop the by itself. Yeah. If we just compare, let's demonstrate this map or this obstacle. Okay. Line by line. So basically, here I'm saying, guys, this is y-axis and this is the x-axis. Okay. Here y is changing from 1, not 0. He just put a 0, just like a coordinate, but there is in actual case there is no 0. Y starts from 1 and x also starts from 1. So we have here y starting that way from 1 to 1300 and x also from 1 to 1300. So I'm saying obstacle if set any location with y less than 50 and or greater than 1250, less than 50 and greater than 1250 equal to true. That will base if I just comment these lines and execute only this line here, it will just create this frame here, this solid frame. Well, let's try that. Let's try that for you. Look. Let's analyze this. I'm saying any cell that has coordinate y less than 50 will be an obstacle. So from all these cells, all these cells here has y less than 50. So y here is 1 or 0. There is no 0 again. So from 1 to 200 to 200. So probably in the middle here is 100. So this is the quarter, which is 50. Any cell that has coordinate y larger than 1250 is also an obstacle. All these cells here has y coordinate larger than or greater than 1250. If any cell has a coordinate less than 50, it's also obstacles. All these cells here on the left-hand side has x less than 50. X here is in the x-axis here, of course. This is 200. In the middle, we have 100. And here is the quarter of 200, which is 50. Any obstacle that has x coordinate larger than 1250 is also an obstacle, which is this one here. Okay, let's take another example. This is not a probabilistic roadmap, by the way, just creating the map, but it's a big one. It's a very big one. So the first line will create this one. Now we want to create this obstacle here. This is easy as well. So I'm saying all these points here are within x equal to 1 and x equal to 200, or x less than 200. Right? And for y, for this axis, all these nodes here are within y equal to 600 and 650. This is quarter, this length here is quarter of that length. So this is 600, this is 800, so this is 650. So any cell that has y less than 650, less than this bar, and greater than or larger than 600, larger than this bar, so within these two limits, it will be an obstacle. And so on. If it's not clear, let me know. I can explain another example. That's fine. Should I proceed?
Is it always greater than like 1 above that number or less than?
So here is this and. All these cells here, okay, has y less than 650 and greater than 600, and the x for all these nodes are less than 200.
Oh no, I was talking about for like the first one, it's y is less than 50, right?
Yeah, those.
Is it basically 1 through 49, right?
Yes,
And not
yes.
50?
Not 50, yeah. You can add it, it will not, you know. I found this example in Matlab. So Matlab has its own, Matlab has a computational motion planning library. So all this probabilistic roadmap, all that code here that is approximately more than 150 lines is actually one line in Matlab. But we don't have the, it's not for free. So you can generate this probabilistic roadmap with just one line, just to define the maximum number of nodes, you know, and even the map. There are maps there, okay. So you can also choose the map, but here we have to do everything from scratch, okay. So now I'm just constructing the map. I'm sorry, I'm just creating the obstacle map. Then we will add our nodes around these obstacles.
Okay.
So when I see the map, when I saw the map on Matlab website, you know, by my eye, I noticed that it's around 50. So it doesn't matter if, of course, if you add less than or equal to So y equal to 50 will be part of the obstacle, but now y equal to 50 is not part of the obstacle. Okay. It's just some example to play with. That's it. Okay. Should I take another example, or I think it's, if it's not clear, just let me know. Okay. So if we just uncomment that. Okay, so that part will construct the map, the obstacles inside the map. Okay, this command here will show it like an image. This is like an image. Im show means image show. So image show is just a function in Matlab that takes a matrix or array, two-dimensional array, and show it in that way here. Then I am axis on means both text here. Text means these numbers. Then I'm adding labels. So this is X label. This is a label here on X. This is another label on Y. You can name it whatever. So you can name it, for example, X axis and Y axis. That's it. That's fine. You can name it whatever. Just a name. No? X, X, Y, X. And you can also put a title, PRM created map, and you just make a grid on, so you can have this nice grid to to follow what was the coordinates of each point you created. Then you define the important parameters that you're gonna fine tune. Okay, so for example, the maximum number of nodes to connect is 2. That means when you generate a new node, you can only connect it to maximum 2 nodes. Given that these 2 nodes are within the range of 350 in that case. And by the way, you may generate node without connecting to anyone because all the close nodes to it are not within the range of 350 or whatever you define here. That's fine. Segments again is when you generate a new node and try to connect it to the closest node to it. Okay, maybe one or more of these nodes or is there an obstacle between the new generated node and that node? So based on the way that I showed you how to check if there is an obstacle or not, you divide this edge into 10 points or 10 segments. And you should check that each point on that line or edge are away or not within an obstacle. And the maximum number of nodes to generate here is 1000. Okay, good. So let's start. Here is just a counter. So this is a counter to count the generated nodes. So basically this counter, its maximum should be 1000. Basically. Here you create the map. So you will take the size of the obstacles and fill it with just zeros in the beginning. Then you fill any point that is true in obstacle with 1. Just like copying obstacle to map. But map obstacle is a Boolean array. It has true or false. Look. True or false. Basically, a free array is false, and obstacle set are true. Then basically we will convert this map into a graph. Okay, so you need some array to represent this graph. So let's do that in on the on PowerPoint. I will just explain what is this graph connections means. So you guys can see my screen, right? You can, I'm sorry, you can see my tablet, right?
We can.
Okay. So basically, so for example, if you have a graph like this, let's assume we just have, you know, 3 cells, 3 nodes. 1, 2, 3. This is your graph now. Very simple one. Okay. So this is the array that we're gonna need. It's an array that has 3 columns. Let's add another one. 4. 3 columns still. And 4 rows because we have 4 nodes. So we have node 1, node 2, node 3, node 4. So each node has an ID. Each node is connected to some other nodes, right? So we need, and as we see here, node 1 is connected to 3 nodes. So at most we need 3 columns. So column 1, column 2, column 3. So this is neighbor 1, neighbor 2, and neighbor 3. Or connection to neighbor 1, connection to neighbor 2. Or what are the nodes that are connected to each one of these nodes? So node 1, for example, is connected to node 2 and node 3 and node 4. 2, 3, 4. So when I read this row here in that array, I will know that node 1 is connected to node 2 and node 3 and node 4. There are edge between node 1 and node 2, another edge between node 1 and node 3, another edge between node 1 and node 4. Node 2 is connected only to node 1. And this is empty. Of course, there is no empty in Matlab arrays. So you can put some values there that represent no connection. Like, for example, infinity. Infinite. You remember, guys, Dijkstra's algorithm and, you know, A star, all that stuff? We use infinity with the same, you know, meaning up there. Then node 3 has 2 connections with node 1 and node 4. 1 and 4. Then infinity here. No other connections. Then node 4 is connected to node 1 and node 3 and infinity. So this is actually a 4 by 4 array. But it doesn't have to be 4 by 4. For example, if we have another node in node 5, which is connected to node 4 only, then this is node 5 here. And it's connected only to node 4, infinity. In that case, it's 5 by 4. Okay? So, what are the number of columns we need? If we set the maximum number of connected nodes to 2, for example. Okay, so basically we have two columns here. Besides this column, so we have max number of nodes, connected nodes plus 1. So max node connect. This variable here is that one, just to make it, you know, this one here. Plus 1. This is equal to the number of columns in that array. We'll call it a graph array because this array now is representing a graph basically. This is how we represent graphs in programming using an array. It's called adjacency matrix. This is called adjacency. I'm sorry if this is wrong. Matrix. Adjacency, I don't know, whatever. Okay. And how many rows we need? the rows we need is actually equal to the number of nodes in the graph. Which in that case, for example, oh, I'm sorry. Sorry, guys. So in that case here, 2000, for example. This is the number of nodes in the graph. So we know it from this parameter that we change ourselves. Okay, this is clear. So let's go back to the Matlab stuff, and you can see the Matlab now, guys.
No.
The slides.
Nope, nope, they don't see it, so that's fine. So let me do it again. Now you can't see anything. Then we go. How about now?
Yes.
Okay. So let's go back to the Matlab. So graph connections is actually the array that I just explained to you on the slides. Okay. How many rows it have? It has max node grid, this one. How many columns? The maximum number of connections plus 1. So in the first column, I put the ID of the node. In the next 3 columns, I will put its connections. If there is no connections, this will be infinity. That's why I initialize it to infinity in the beginning. Okay. Then we go again into a while loop. This while loop will continue as long as we have less number of, as long as nodes is less than the maximum number of nodes that we should generate and represent the graph with. Once I have 1000 node based on that parameter here in my map, that's it. I will just exit this while loop. Okay, so we just follow the algorithm that I just showed you in the slide. First, generate a random node. Okay, so basically this node that we will generate, it should be within the map. So it has coordinate in x between 1 and 1300, and it has y coordinate also between 1 and 1300. This is how to generate a random integer, okay, in Matlab. You put here the maximum number, and here you put rand I. This is a function that generates random integer, rand I. Rand I of whatever means generate integer between 1 or 0, and this whatever, okay, maximum number. So basically the coordinate x of the new random nodes that I will generate should be between 1 and, I'm sorry, 1, not 0. And this number of columns. Remember from last time, x represents the number of columns. And the y coordinate, again, random integer between 1 and the maximum number of rows. If this node is an obstacle, generate a new one. That's not a valid one. Don't consider it. So we'll just continue and we will not do anything. We will not connect it to anything because it's part of an obstacle. For example, if you generate, for example, a node here in that location, it's not valid because it's belonging to an obstacle. Also, if it was a previous generated node, then it will be redundant. So no need to generate this a node in the same location again. And here we mark the obstacle with 1, but after a while, after just some lines, we will mark, if we generate a node and this is a valid node, we will mark it by 2 in the map. Okay. So map now has 0, which means a free cell. one, which means obstacle, or two, and that means there is a point here that we generate, a node here that we generated. Okay. Once you pass this condition, then I don't know. That's actually wrong. It's cancelled. Once you pass this condition, that means this node is not generated before, or it's not an obstacle, part of an obstacle. Then you it's a valid node. Then you increase this counter because you generated a new valid node now, and you mark it by 2. So in the future, if you generated the same point again, you just exclude it because we have it already. Then we just draw it. We will draw it as an asterisk in our map here. And to draw a point on a map, and by what I mean by a map here is something that you draw using image show. To plot something inside the same image show, this one here, you plot it in that way, node X, node Y. And we plot it in red, and it will be like an asterisk. Okay. Then we search for the nodes within the range. The range of what here? The range of 350. Any node within 350 around this node can be considered as, it's a candidate to be connected to our node. We will choose afterwards only 2 nodes of them, 2 nodes between these nodes to connect our new node to them. Okay, how we gonna get these nodes that lie within the range of 350 meters? That's not hard, because any node that we will generate, we will store it in the graph connection array. So this graph connection array is an array that contains all the nodes that we discovered or generated, I'm sorry, and their connections as well. So we loop over all the nodes inside this array. Remember, for example, if you have 2 entries, for example, you have only 2 rows, then all the other rows will have infinity. So you will stop once you reach one of these nodes that's not discovered yet with infinity. You get the row and the column of that node. Then you check the distance between them. If you have two nodes or 2 points in space, each one has its own X and Y coordinate, then the distance between these 2 nodes are actually the norm. You guys remember the norm from last time? Square root of X minus X square plus Y minus Y square. This is actually the distance between any two nodes or points in the space with Cartesian coordinate, X and Y.
Professor, real quick, what is that num1 that you have in the for loop?
This one?
Yeah.
Yeah. So null means null. No, not num1. Null. Number of elements. Number of elements. Number of elements in the
Makes
first column in this array. And what are the number of elements in the first column of that array? It's 1000.
Right. Okay, I got it.
But some of them are infinity. Infinity means something that is not added yet to the graph array or graph connection array.
Right.
So we break it when we discover one of those unfilled rows, we can say. Okay. Okay. Yeah. Now, okay, let's assume that we check, for example, let's assume this is the first node in the graph array, okay, and this node is within the range 350, but maybe I cannot connect to this node. So here I am checking that. So this via obstacle is a function. Actually, this function, I will not show it to you because you will implement it yourself. This via obstacle array is actually an array. I'm sorry, it's via obstacle. It's a function. Okay, and this function is just one moment, guys. Yeah, thank you. It's a function that I created. It takes the map. It takes the number of segments, the number of points that I will divide the edge that I want to check if it's crossing an obstacle or not. It takes the node that I created. This node has y coordinate and node x coordinate and node y coordinate. And it takes also the coordinate, row and column. And remember, row is actually the y and column is actually the x of the node that I'm checking against, the neighbor. And if this edge is passing through an obstacle, then I will just skip that. I will go again and check another neighbor. Okay. If this function returns false, then yeah, this node, this neighbor is within the range, and I can connect it. I can put an edge between the new created node and that node. Okay, without crossing any edges. Okay. Okay. So no, yeah. And if according to what I said, if we pass this check here, if this function returns false, then I can connect to that node. So I will put it in an array. So just bend this new node, the node that we are checking right now, to that array called nodes to connect. Okay. And also put the distance between the new created node and this neighbor inside this. Also, how can I say this? Another array, okay, in which we put the nodes that we can connect to, and it's the distance between the new created node and that node, that neighbor, we can say. Here we put the ID of the nodes that we can connect to, and here we put in the second cell, we put the distance between the nodes that we are exploring around and the neighbors that we can connect to. Okay, and we continue in that loop, for loop, until we finish testing the current node to all the nodes in the graph that all the nodes in the graph, all of them, actually, all of them. Okay, but again, we cannot connect to all the nodes. We should connect to maximum 2 of them, for example. So I will choose two of these nodes only inside. I'm sorry, where is it? Yeah, 2 of the nodes that inside this array to connect to, and that's what I will do here in that piece of code. So let's see. So while the size of distance is larger than 0, that means there are nodes that I can connect to inside this array. If this array is empty, that means the new created node are not cannot be connected to any around the node because there is no nodes in that array. Then I will sort the elements inside this array based on the distance to the start node. Okay, and that's very nice function in Matlab can do that for you. So let's try this sort array. Assume that we have an array in Matlab like this. So let's assume that we can connect it to 3 nodes. The first node has an ID is 1. The ID of the first node is 1. And the distance between the node the new created node and that node called 1 is, for example, 50. Okay. We also can connect to another node called 72. The ID of the second node is called 72. And the distance is, for example, 25. We also can connect to a third node, which is, for example, has an ID, for example, 60. And it's, or make it 80, that's fine. And the distance is, for example, let's say 10. Okay. Look, guys, this is the array called A. So I want to sort this array based on the second column. So this will be the first row because the second column has its minimum in that row. So the first row should be 80 and 10. The second row should be 72 and 25. The third row should be 1 and 50. So all what you need to do is sort rows, the name of the matrix or array, which is A in here, and which column you want to sort the array based on. Here we want to sort based on the second column. So put 2. Boom. Look, guys, this is what we want. This guy becomes the first row. This guy becomes the second row. This guy becomes the third row. Okay. So here you order the row based on the values in the second column. That's exactly what we want here. So this array called distances, let's call it another beautiful name, ID distances, because the first element is the ID of the node. The second element is actually its distance from the node that we generated. Okay. Then we make a for loop to loop over the elements inside that array based on, and we will stop this for loop based on the comparison between the minimum number of nodes that we want to connect to or the size of that array. So for example, this array, I'm sorry, yeah, so distance is sorted, has, for example, one row, and the maximum number that we can connect to is 2. So basically, since this array has only one row, so basically you can connect only to one element, not 2. So I must stop after the first iteration. So I shouldn't make I equal to 1 to 2. At the same time, it may have, for example, 4 nodes, while the maximum numbers that I can connect to is just 2. So I must stop after 2 iterations. So I will iterate from 1 until the minimum number between these 2 numbers, the maximum number of nodes to connect to, or the size of this array. Okay, guys. So this array will have the nodes sorted. So this, for example, here based on that example, node 80 is the closest to me. So I will make an edge between 80 and the new created node. So I added this as I added here. Then I will loop again, okay, and add the second node into I equal to 2 that time. Okay, then here I am drawing the edge between the new node and the closest node. So let's run this step by step. So let's have a breakpoint here. I will also, yeah, there is no other breakpoints. That's good. Let's run from the beginning. Okay, that doesn't matter here. Okay. So let's see what's gonna happen. Yeah. Let's have another node. So basically, sometimes I generate nodes, but I can't connect them to anybody. That's why I don't go into that loop, okay? Because this array is actually empty. For example, this node here, all its close neighbors are far away from it. So we can't connect it to anybody. So this array will be empty. That's why we didn't go into that part of the code. Okay. Yeah, we generated that node here. We connect it to this one. I don't know if we can connect it to another node or not. Let's, yeah, we can't connect to any other node. Let's have another node. This one here. Basically, this one will be connected to this one. And it will be connected also to this one. Okay. Let's have another example. Boom. We have here a node here. This is basically be connected to only one node, which is this one. Let's see. Yeah, only one node. You see, guys, only one node that will be connected to. So we will have one iteration. And boom. Good. So let's have another example. This node. This will be connected to probably two or maybe three, but I'm not sure if this is part of the. We will see. We will see. Let's. Yeah, only three nodes. It will be connected to three nodes. This one, and also this one. Let's see one by one. Good. Good. Yeah, these two nodes in the beginning because it's closer to this node than this one. It was only two. Okay, yeah. Then you continue again. Have another example. Is this one right? Yeah. Let's see. Two nodes. Good. Then good, and that's it. This node here. Good. Good. And that's it. You get it, guys? Is it clear? So don't worry about this, for example, node, because it's not actually now the graph is being connected. Okay, maybe looks now ugly and doesn't, you know, if we want to stop at that point, yes, we have very small memory to use because we have how much? We have 5, 7, 11, 12, 15 nodes. Okay, but basically we can't connect. The graph is not connected together. Okay, So the robot will not be able to navigate. That's why we need, to generate more and more nodes in order to have better coverage, and the robot can go everywhere, we can say. So let's have one last example. I don't know which. I don't know, where is this node? Yeah, this one. I think this one. We'll see now. Yeah. Yes. Okay. Let's now make like this. Yeah. Just after. Okay. That's good. So let's let's play with some of the parameters. So for example, let's make this 1000. Oh, let's make this 20. Let's see what's gonna happen. Let's have also a breakpoint here. That's very good place for the breakpoint actually. And let's see how the map is evolving. It's really nice. Actually, I can see we can stop at that point, okay? Because it looks like we could cover all the locations. This map is just like how can a 4-bedroom, for example, house or home. Okay, you have a bedroom here, we have another one. So basically, we could cover now most of the locations inside this map. Okay, and this is the trade-off that I'm saying to you. If we choose some parameter, more than enough, you may end up using a lot of resources, a lot of memory, for example. Okay, but you may have, of course, a better shortest path or a better coverage. Let's continue. So each new generated node can be connected to 20 nodes. That's why for each new node we generate, we may have up to 20 extra edges in the map. That's why it will looks like very, very dense. It's like a spider net, right? Well, that's it. Continue forever. Yeah, that's it. This is the final phase. Okay. Let's now, play with very important parameter, but I will show the effect of it. This segment variable here, this parameter. If the more this parameter is, I mean, the more the value, the more and more checking you will do. Okay, so let's go back to let me show that on the tablet. You can see my tablet, guys?
Yes.
Yes.
Good. So let's go to the final. Yeah, let's do that here. Okay. So we have here the nodes, a new node, and here is the obstacle in between. Okay. So this should be, if there is an edge, of course this is wrong, but it will be something like this, crossing the obstacle, which is of course wrong. Let's see the importance of that number of segments. So if we choose this number of segments equal to 3, so we'll divide this edge into 3 segments, right? So let's do that. Or 3 points. 1 and 1, like. So we have 3 segments. This segment, number 1, segment number 2, segment number 3. But how many points now we have? How many points we will check? We will check this point and we will check this point, right? This point is not part of the obstacle. Okay? And this point is also not part of the obstacle. So because you choose a very small number of the number of segments, these parameter segments, of course you will process fast because you are processing less number of segments, we can say, or points on the segments. But you may judge this incorrectly because based on that we have only 2 nodes to check, and both are outside the obstacle. So you may judge and say that the program, of course, will say that, or the robot will say that, oh, there is no obstacle, so I can connect an edge like this. You got my idea? It's a trade-off. Faster processing versus accuracy. Or even right and wrong. This is a fatal mistake.
So
Yes.
you want to create your segments based on like how big your obstacles are?
That's, yeah, you should be smart in that way. You should say, yes, that's right. You should consider, you know, it's a parameter basically it's a parameter that you play with, okay? But there is no rule, like what you are saying. There is no rule for it. How many, you know? So basically choose it. You may say so, but how can I say that?
Because I do understand how it works, but I was just
Yes. The metric that you mentioned is a good metric. I know. So, for example, if the obstacle, you know, in that with that width, for example, yeah, you may, for example, choose the segment, for example, equal to half of that width, so that you are sure that one of the points will be on that on the obstacle. Okay, that's good. So if we do that, so we'll have something like this. Okay, and yeah, now 2 points now are part of the obstacle. That's a good metric that you mentioned, the one that you mentioned. Okay, so let's do that. So let's make it 1, not 10. And let's see what's gonna happen. And let's make this 2 like what it was. And let's see what's gonna happen.
oh, we can't see the screen.
Oh,
Yeah.
I'm sorry. Okay, I will do that. Can you see the Matlab now?
Yes.
Okay. So I made this segment, instead of 10, I make it 1. And this is 2. So we will see the first one, not this one. So let's see what's gonna happen. Yeah. It's very, you see, guys? Of course, these are not valid, right? Again. So this is the importance of that parameter called segments. Clear, right? If it's not clear, just let me know.
And where do we place the segments on that line exactly? Or is it? You
divide. So basically, if you choose, so let's go. We have here the example. We have, so for example, if the length of this is, for example, 50,
Mm-hmm.
and you have this is equal to 10, then you divide the 50 by 10, it will be what? It will be 5. So you will have 5 segments or 4 points, right?
Right.
Yeah. Then this will be your homework. After the deadline, no, the deadline. So the deadline for the fresh, so you have 2 weeks. The first week, you know, you will submit and you get the maximum score. After the first week, you have another week. You can submit, but it will be late. So at the beginning of the second week, I will publish a video showing you the idea, just like what I did with breadth first search and depth first search. Okay, it's very actually I gave you the idea, but I will make it more detailed. We can say, so you can just take my words and, you know, but it's easy just to think about it. You should think. Okay, it's really simple. Okay, so yeah, so we make it 1 and it was bad. So let me check. Yeah, let's make it 20. Of course, with 20 it will 10. There was no so we started with 1. With 1 there was some crossings, invalid edges. Let's make it 2 and see what's gonna happen. What happened here? This should be, oh, I'm sorry. This guy. Okay, this is the one that shows. Okay, so we have crossing. So let's make it 2 and let's see. Yeah, still, but less now. Less number of crossings. Let's make it 3. Yeah, you have only 1 crossing. This is the only crossing now. Oh, I'm sorry. Yeah, it's 3. But in the beginning, there were more than this. Now it's just 3. So let's make it 4. With 4, there is no crossings. Okay. So 10, it was more than enough, we can say. That's what I'm saying. If you choose 10, you are too conservative, okay? You will most probably end up with a map with no violations, but you make some extra redundant processing, which takes more time. But with 4, less than the half of 10, okay, you are still getting a valid map with no violations at all, okay, but with less time as well. Okay, this is a thing called fine tuning. All algorithms in robotics need this kind of fine tuning. Okay, parameters that many of them, not all of them, many of the algorithms in robotics need this kind of fine tuning. Okay, this is one of the parameters that you can fine tune. Okay. Okay, guys, is it clear? So your homework that I will publish, okay, is basically is to construct this function here that I'm hiding from you, okay, which only checks if the edge is crosses an obstacle or not. Basically, we'll implement what I said to you. Divide the edge into segments, okay, and check the points between the segments if they are on the obstacles or not. Okay, and try to play around. Okay, change this what? I'm sorry, this parameter here, okay, and you know you can easily, you know, implement. I hope so. It will be easy for you. It's easy, okay. I will not give you something hard. Okay, guys, any question you have?
Can you go to the bottom? I wanted to see or talk about something.
Bottom here or the code?
Like line 98, why do you have it as distances and then the semicolon? Is that just to make 2 rows
Okay, so
in this array?
semicolon means, okay, let me do it on the tablet better. Yeah, I'm sorry, without anything. So let's do it here on the what do you call this? The space or whatever. Okay, so let's have a P empty array. Okay, so B equal to the old B and add to it a new row. Okay, then add a new row, let's say for example 5 and 3 with a semicolon. This would be the second row. Look, 1 3 in the first, then this would be the second row.
Okay,
let's do it with a comma because there is a difference here. Okay, let's do it with the comma. So let's have a new array C, comma 1 and 2, then C again with 3 and 4, whatever. This should be no new row. It will be the same row.
right.
Look.
Okay.
So with semicolon, you are adding, as a new row,
Okay. Thank you.
Okay.
And also for it's because I'm kind of getting a little bit confused on how line 109 is working.
Line 101?
109 because you have it.
109. This one. Yeah.
Yeah.
Yes.
The min is kind of throwing me off, like the max nodes connect and then comma and then the size.
Yeah, I am saying minimum of this number and this number.
Okay.
So basically this number is 2. Max nodes connect. Okay. And this number this is another number. Say I am saying here size of distance sorted. This is an array. Okay, this is an array that has number of columns and number of rows. Okay, look, let's go here to this. You see this C array. So let's add another column to. You remember this array B?
Right, 2 rows.
Yes, this B. So let's do that with B. So B is actually equal to that. Okay, this is B, for example. B is, it has 3 rows and 2 columns, right?
Right.
Good. Size of B, it will return what? 2, 3, 2.
All right.
3 rows and 2 columns, right? Now, what is the minimum? I'm sorry. Yeah, 3, 2. Look, if you want the rows only, you want the first one. So do that. If you want the column numbers only, or the column size, this one, which is the number 2, so you do that. Oh, still confused?
No, I got it.
Okay. So that's what I'm doing here. So this array may have, for example, 5 rows. That means that there are 5 nodes within the range around the new created node. But we want only 2 of them. Okay. How to know this has 5 rows? Make it size of this node and 1. So this will return the number of rows, which is representing the number of nodes within the range that I can connect it to.
Right.
Okay. It's a very easy code. You just need to implement. Oops, to implement that one. I will remove it in the video. That's fine.
Yeah. Okay.
Okay. Okay, guys. Any other question?
Dr. Mustafa,
Yes.
I just wanted to ask if it's possible to extend the due date for the A star C++ just for like the weekend.
You have exam?
I have 2 exams next week, fields and waves and probability theory.
Mhm.
It would be kind of
Okay.
nice if we could possibly get an extension, because I really want to study for those 2 midterms next week.
So we can make it until look, I can mark the late note from half 75. So if you got 10, I will make it 7.5 because I am sure it's easy. It's a very easy one. The A star algorithm is very easy. Just look at the MATLAB and convert the MATLAB into C++. So my offer is that I will keep the due dates, but I will mark the late submissions out of 75% of the maximum mark.
Okay, that's fine. Thank you.
And could you make it available for longer, because it's gonna end on the 10th and we will no longer be able to turn it in.
That's what I'm saying. That's what I'm saying.
Oh, okay.
Okay. Okay. Any other question, guys? Okay. Thank you very much. See you on Monday. Bye-bye.